You may ask yourself, why would anyone want to mash meshes in a mush to mish the mush? Well, in my case, it's all about performance. Just take a look at this. When I create a hexagonal grid of a radius of 100 with my previous setup, Unity takes about 3 seconds to build it. When I do it with all my meshes mashed into one big mesh mush, it is done pretty much instantaneously. Not only does it build my grid faster, but when zooming out and moving the camera around, there is a pretty significant difference in frame rate, which only gets worse the bigger the radius gets. So what is happening? Well, my first method would create a game object with a sprite renderer and a collider for each of the grid dots. I noticed pretty quickly that this wouldn't scale well beyond the 100 radius grid. My first instinct was to assume that it was the colliders that were hindering performance, but after doing some profiling, I noticed no noticeable difference when removing the colliders. Then, it dawned on me that it was probably the amount of unique meshes that were being rendered by my sprite renderers. In the case of a 100 radius grid, that would be 30,000 meshes. So I ventured to mash the meshes in a mush to mish the mush. Mashing meshes in a mush to mish the mush. Mashing meshes, mish a mush, mush, mush. My original setup would first calculate the positions of all the grid points, then it would spawn a dot prefab in each of these locations. Each one of these prefabs was a game object with a sprite renderer holding a circle sprite, a circle collider 2D to detect clicks, and a dot script which handled on-click events which point to my pencil class. One thing to note is that my sprite and my circle collider are of different sizes, which really helps improve the user experience by giving a bigger click area than the actual visual dot size. In order to make my new setup work, I would need to create one big visual mesh and change my click detection system. To create the visual mesh, I first calculate my grid positions the same way as with my original setup. Then, I create a game object with the required setup to render a mesh, which means adding a mesh renderer, a mesh filter, and a new mesh which I set on the mesh filter. I also made sure to add a material to my mesh renderer and to set my mesh's index format to 32-bit to be able to have more than 65,000 vertices on it. Once that's done, I proceed to generate the vertices and triangles for that mesh. For this, first I create a circle mesh. While I could have used the original circle sprite, I opted to use my polygon renderer method to be able to increase or decrease the amount of sides for my circles as desired. Once I have the vertices and triangles of one circle, I create a grid vertices and grid triangles list. Then I loop through each position and add one copy of my circle's vertices per position, while offsetting the values by that set position. I also add one copy of the circle's triangles per position, while offsetting their values by the amount of vertices in the mesh previous to that position. This makes it so that the new triangles point to the new vertices indexes and not to the ones on the first set of vertices. Once I add all my vertices and triangles to my lists, I simply assign them to my mesh's vertices and triangles. As for my click detection, I first thought of creating a big mesh holding all my colliders, but it really didn't make sense since the dot script would pass on the position of the game object, and having one big collider mesh meant not being able to do that. So instead, I made a mouse controller script which detects clicks, constantly calculates the nearest grid position to the mouse, and calls the pencil methods using that position. Turns out that finding my closest grid position was probably the most difficult part of this whole process. Mashing meshes in a mush to mish the mush. Mashing meshes, mish a mush, mush, mush.